Across the quiet span of cosmic history, the search for living systems beyond a single familiar world has unfolded as a patient accumulation of observation, reflection, and careful inference. The night sky has long been understood not as a static ceiling, but as a deep layered environment where matter organizes under consistent physical principles. Within this environment, planets form around stars through processes that appear to be widespread and repeatable. From this foundation, the idea that chemical systems capable of sustaining organized activity might arise elsewhere has been approached without haste and without presumption. Early astronomical surveys revealed that stars differ in mass, temperature, and longevity. These variations influence the regions around them where energy conditions remain moderate enough to allow complex chemistry to persist. Such regions have been described as zones of temperate balance, where molecular structures can remain stable over extended durations. The recognition of these zones did not imply that life must arise within them. Rather, it established a framework for narrowing attention toward environments where known physical constraints do not immediately prevent biological processes. As instruments improved, the detection of planets beyond the solar system became a matter of indirect measurement and statistical confirmation. Minute shifts in stellar motion and subtle changes in observed brightness indicated the presence of orbiting bodies. Over time, these detections accumulated into catalogs that demonstrated planetary systems to be common rather than exceptional. Within these systems, worlds of varied composition emerged, some dense and rocky, others dominated by gas and ice. The diversity of these worlds suggested that the conditions leading to planetary formation do not converge toward a single outcome. Instead, they generate a spectrum of environments shaped by local history and material availability. Parallel to astronomical discovery, developments in chemistry and biology refined understanding of how living systems maintain structure. Life, as currently understood, relies on networks of reactions that regulate energy flow and preserve internal order. These networks depend on solvents, molecular building blocks, and gradients that allow reactions to proceed in a controlled manner. Water has been recognized as an effective medium for such processes due to its thermal properties and capacity to dissolve diverse compounds. Yet the recognition of water as favorable did not exclude the possibility of alternative solvents operating under different conditions. Laboratory studies have shown that organic molecules can form under a range of temperatures and pressures. Simple compounds exposed to energy sources can assemble into more complex arrangements without guidance. These findings support the view that chemical complexity is not fragile. It can arise naturally where energy and matter interact over time. In planetary context, surfaces, atmospheres, and subsurface layers provide settings where such interactions may persist. The study of extreme environments on Earth has further expanded the boundaries of expectation. Organisms have been observed thriving in conditions once thought prohibitive. High salinity, intense radiation, and limited nutrients do not uniformly prevent sustained biological activity. These observations do not suggest that life is ubiquitous. They indicate that the range of viable conditions is broader than previously assumed. When these insights are applied cautiously to planetary science, they inform the selection of targets for observation. Remote sensing techniques analyze the composition of distant atmospheres by examining how starlight interacts with gases. Certain combinations of gases can reflect ongoing chemical processes that require continuous replenishment. When such combinations appear together, they warrant careful scrutiny. They do not serve as confirmation. They serve as prompts for deeper analysis. The interpretation of atmospheric signals must account for geological and photochemical mechanisms that can mimic biological effects. This necessity reinforces a conservative approach grounded in multiple lines of evidence. Exploration within the solar system complements distant observation. Robotic missions examine planetary bodies that may harbor subsurface environments shielded from surface extremes. Ice-covered moons with internal heating present scenarios where liquid layers may persist beneath solid crusts. Within these hidden regions, chemical gradients could exist over geological timescales. The presence of energy sources and essential elements supports the plausibility of sustained chemical activity. Yet direct detection remains constrained by technological and logistical limits. Sampling such environments requires precision and patience. Progress in this field has been incremental. Each mission refines models and informs subsequent designs. Throughout this process, language has remained measured. Terms describing potential life are framed in probabilities and conditions rather than declarations. This restraint reflects an understanding of the complexity inherent in defining life itself. No single characteristic suffices. Life is recognized through patterns of organization, interaction, and persistence. As research advances, definitions may evolve to accommodate forms not yet observed. Until then, inquiry proceeds through careful alignment of theory, observation, and experiment. The accumulation of evidence across disciplines builds a coherent picture of possibility without asserting inevitability. In this manner, the search continues as an extension of natural science rather than a departure from it. Grounded in known principles yet open to revision, the quiet persistence of this effort mirrors the slow rhythms of the cosmos itself. A process unfolding over long intervals, guided by observation and tempered by humility. As observational capability extended beyond the initial discovery phase, attention gradually shifted toward characterization rather than enumeration. Understanding the physical and chemical properties of distant worlds required a convergence of astrophysics, atmospheric science, and statistical modeling. Light passing through or reflecting from an atmosphere carries subtle information encoded in absorption patterns. These patterns arise when molecules interact with specific wavelengths according to stable quantum rules. By comparing observed spectra with laboratory references, researchers infer the presence of gases such as carbon-based compounds, nitrogen-bearing species, and simple oxidants. Each identification is probabilistic, derived from signal strength, noise modeling, and instrument calibration. Confidence increases when independent observations converge on consistent results across time and method. The environments under examination are not isolated systems. They exist within stellar contexts that shape radiation exposure, particle flux, and long-term stability. Stars evolve gradually, altering luminosity and magnetic behavior. These changes influence atmospheric retention, surface temperature, and chemical equilibrium on orbiting planets. Thus, assessments of potential habitability incorporate stellar age and activity alongside planetary mass and composition. Planets with insufficient gravity may lose atmospheres over extended periods. Those with excessive mass may retain dense envelopes that suppress surface interaction. Between these extremes lie worlds where solid surfaces, liquid phases, and dynamic atmospheres may coexist. Such balance is neither rare nor guaranteed. It depends on formation history and subsequent evolution. Theoretical models simulate these processes using initial conditions drawn from observed systems. Results suggest multiple pathways toward temperate states. None imply certainty of biological emergence. They outline scenarios where chemistry can proceed without immediate constraint. Within these scenarios, time plays a critical role. Chemical networks require duration to explore configuration space and stabilize feedback loops. Short-lived environments may never progress beyond simple reactions. Long-lived settings allow accumulation, modification, and recycling of molecular structures. Geological processes such as volcanism, tectonic cycling, and erosion contribute to this persistence by renewing surfaces and redistributing materials. On planets lacking such activity, chemical gradients may dissipate and stagnation may occur. Comparative planetology draws from terrestrial examples to inform these interpretations. Earth history reveals extended intervals where life remained microbial and subtle in its planetary impact. For much of this duration, atmospheric composition reflected abiotic and biotic contributions that were difficult to distinguish. Only after substantial accumulation did certain gases become globally detectable. This observation tempers expectations regarding remote biosignatures. Life may exist without producing signals readily observable across interstellar distances. Accordingly, absence of evidence is not treated as evidence of absence. It is recorded as an unresolved state pending further refinement. Instrument development continues to prioritize sensitivity, stability, and spectral resolution. Space-based observatories reduce interference from local atmospheric effects, enabling clearer measurements. Future designs aim to directly image planetary surfaces by suppressing stellar glare. Such techniques require precise alignment and adaptive correction. Their implementation represents an incremental extension of existing methods rather than a conceptual leap. Parallel to observational progress, experimental work explores alternative biochemical frameworks. Researchers examine how information storage, catalysis, and compartmentalization might occur under varied chemical regimes. These studies do not propose exotic life forms as expectations. They establish boundaries of plausibility grounded in chemistry and thermodynamics. By mapping these boundaries, scientists refine criteria used in target selection and data interpretation. Throughout this endeavor, language remains intentionally reserved. Findings are contextualized within error margins and alternative explanations. Consensus emerges slowly through replication and review. This deliberate pace reflects the recognition that claims regarding life beyond a single world carry significant interpretive weight. Thus, the process remains methodical, cumulative, and open to revision, advancing through careful accumulation rather than decisive declaration. Within the broader framework of planetary investigation, attention has also turned inward toward the conceptual tools used to define detection thresholds and interpret ambiguous signals. Detection is not a single event, but a layered process involving signal acquisition, noise reduction modeling, and contextual comparison. Each layer introduces assumptions that must be examined and constrained. Statistical confidence emerges through repetition and cross-validation, rather than isolated measurement. In this environment, conservatism is not hesitation but methodological discipline. Signals that appear promising are subjected to alternative explanations grounded in known physical and chemical behavior. Only when these explanations fail to account for observed patterns does discussion proceed toward biological relevance. This approach reduces the likelihood of misattribution and preserves coherence across disciplines. At the same time, it slows the pace of interpretation, ensuring that conclusions remain provisional and revisable. The instruments employed in these efforts operate at the limits of sensitivity. Minute variations in photon counts are translated into meaningful data through calibration against stable references. Thermal fluctuations, mechanical drift, and background radiation are continuously monitored and corrected. These technical considerations shape the cadence of observation and the reliability of long-term datasets. As archives expand, longitudinal analysis becomes possible, allowing trends to be distinguished from transient artifacts. Such temporal depth is essential when evaluating environments that evolve over extended intervals. Planetary atmospheres may undergo cycles driven by orbital variation, internal processes, and stellar influence. A single snapshot cannot capture this complexity. Thus, sustained observation programs are prioritized despite logistical challenges. Within the solar system, sample return missions represent another avenue of inquiry. Material collected from planetary surfaces or atmospheres allows direct laboratory analysis under controlled conditions. Isotopic ratios, mineral structures, and organic composition can be examined with precision unattainable through remote sensing. These analyses inform models of planetary history and chemical evolution. They also refine criteria for identifying non-biological processes that can generate complex organic compounds. Understanding these processes is critical for distinguishing background chemistry from potential biological modification. The lessons derived from nearby bodies are applied cautiously to distant systems. Analogies are treated as heuristic rather than definitive. Differences in scale, composition, and history are acknowledged explicitly. This careful transfer of knowledge maintains internal consistency across research domains. In parallel, theoretical work addresses the emergence of complexity as a general phenomenon. Complex systems arise when interacting components follow simple rules under sustained energy flow. Feedback loops stabilize certain configurations while suppressing others. In chemical contexts, this can lead to self-reinforcing networks without invoking living processes. Recognizing these dynamics prevents premature attribution of organization to biology alone. It also clarifies the additional criteria required to infer life, such as adaptive response and information persistence. These criteria are challenging to detect remotely and may manifest subtly, if at all. Consequently, the search strategy emphasizes accumulation of converging indicators rather than reliance on singular markers. Educational frameworks within the scientific community reinforce this perspective by emphasizing uncertainty quantification and transparent reporting. Results are shared with explicit acknowledgement of limitations and assumptions. Peer review serves as a mechanism for refining interpretation and identifying overlooked variables. Through this iterative process, collective understanding advances incrementally. Public communication of findings mirrors this restraint by avoiding definitive language where evidence remains incomplete. This consistency supports long-term credibility and aligns expectations with methodological reality. As research continues, the boundaries between astronomy, geology, chemistry, and biology become increasingly permeable. Interdisciplinary collaboration enables more holistic modeling of planetary systems. Such models integrate surface processes, atmospheric dynamics, and potential subsurface interactions. They do not predict life. They delineate environments where sustained chemical activity is plausible over extended durations. Within these environments, life as understood could arise, or alternative forms of organization could persist. The distinction between these outcomes remains unresolved, yet the capacity to frame the question with increasing precision represents progress in itself. The search advances not toward closure but toward clarity, refining the conditions under which meaningful answers may eventually emerge. As inquiry extends further, the role of time scales becomes increasingly central to interpretation. Planetary systems evolve across spans that far exceed human observation windows. Processes relevant to chemical organization unfold slowly under stable conditions, and may reverse or stall when stability is disrupted. Understanding this temporal dimension requires integrating astrophysical chronology with geochemical cycling and atmospheric retention models. Stars progress through phases that alter energy output and particle emission. These changes can either preserve or erode conditions conducive to sustained chemistry. Planets that remain within moderate energy ranges for extended intervals offer greater opportunity for complex reactions to accumulate. Duration alone is insufficient, yet without it pathways toward organized systems are constrained. This recognition shifts emphasis from instantaneous habitability toward long-term environmental continuity. Geological records on Earth indicate that stability punctuated by gradual change allowed chemistry to explore diverse configurations. Abrupt shifts imposed selective pressures, but did not eliminate underlying processes. Translating this insight to other worlds requires caution. Each planet possesses a unique history shaped by formation, dynamics, impacts, and internal differentiation. Nevertheless, the principle that continuity enhances complexity remains broadly applicable. In modeling distant systems, researchers therefore assess not only present conditions, but inferred past states. Orbital mechanics provide clues to historical climate variability. Resonances, eccentricity shifts, and axial stability influence energy distribution across planetary surfaces. These factors modulate temperature gradients and chemical transport. A planet with extreme variability may cycle through phases that intermittently permit complex chemistry. Whether such intermittence supports persistence remains uncertain and is treated neutrally within current frameworks. Atmospheric escape mechanisms further complicate these assessments. Interactions between stellar radiation and upper atmospheric layers can gradually strip volatile components. Magnetic fields may mitigate this loss by deflecting charged particles. The generation of such fields depends on internal dynamics, including core composition and rotational behavior. Thus, internal structure indirectly influences surface and atmospheric chemistry over time. This interconnectedness underscores the necessity of systems-level analysis. No single parameter determines outcome. Instead, outcomes emerge from interaction among many variables operating across scales. In evaluating potential biosignatures, researchers therefore contextualize signals within this broader system behavior. A transient chemical imbalance may reflect episodic geology rather than sustained biological activity. Repeated detection across time enhances interpretive weight. Absence of repetition reduces confidence without negating possibility. Data archives grow accordingly with emphasis on temporal coverage. Technological strategies prioritize revisiting targets to establish baselines and identify trends. These strategies require long-term commitment and international collaboration. Such collaboration distributes observational resources and standardizes analytical methods. Consistency across datasets supports robust comparison and reduces interpretive divergence. Within laboratory, simulation experiments complement observational efforts by reproducing planetary conditions under controlled parameters. These experiments explore reaction, pathways, energy coupling, and molecular stability. Results inform models but do not dictate them. They provide boundary conditions rather than predictions. As these boundaries are refined, the parameter space associated with plausible chemical organization becomes clearer. This clarity narrows focus without excluding unanticipated outcomes. Throughout this progression, epistemic humility remains a guiding principle. Unknown variables are acknowledged explicitly, and assumptions are revisited as new data emerge. The absence of definitive detection is not framed as failure. It is recognized as a reflection of the complexity inherent in the question. Progress is measured through improved resolution, reduced uncertainty, and enhanced coherence across explanatory models. In this sense, proximity to finding life is not a spatial metric. It is a measure of conceptual alignment between observation theory and methodological rigor. As alignment improves the capacity to recognize unfamiliar forms of organization, increases even if such recognition remains hypothetical. The search thus advances quietly through refinement rather than revelation, sustained by patience, disciplined inference, and an acceptance of extended timescales as intrinsic to the endeavor. As methodologies mature, attention increasingly encompasses the socio-technical structures that govern how evidence is gathered, preserved, and interpreted. Scientific infrastructure operates as a stabilizing medium, maintaining continuity across generations of inquiry and allowing incremental gains to accumulate without distortion. Standardization of data formats, calibration protocols, and analytical pipelines ensures that observations made at different times and with different instruments remain comparable. This continuity is essential when signals of interest may be subtle and dispersed across long intervals. Repositories curate raw measurements alongside processed products, enabling independent reassessment as techniques improve. Such reassessment has precedent within multiple scientific domains, where earlier data gained new relevance when examined through refined theoretical lenses. In the context of life detection, this practice guards against premature closure by preserving openness to reinterpretation. Equally important is the cultivation of negative results as informative outcomes. When extensive surveys yield no corroborating indicators within certain parameter ranges, those ranges become constrained with greater confidence. Constraints sharpen models and redirect resources toward unexplored regimes rather than reinforcing untested assumptions. This disciplined allocation reflects an understanding that discovery space is finite and must be navigated efficiently. Instrument proposals are evaluated not only for sensitivity, but for complementarity, ensuring coverage across wavelengths, temporal scales, and target classes. Such diversity mitigates systemic bias and reduces the risk that entire categories of phenomena remain invisible due to methodological homogeneity. The training of researchers reinforces these values through emphasis on statistical literacy, uncertainty propagation, and critical evaluation of priors. These skills support cautious interpretation, especially when public interest amplifies the perceived significance of findings. Communication strategies within the scientific community prioritize clarity of scope and limitation. Terms describing potential biological relevance are carefully qualified to avoid conflation between detection and interpretation. This internal discipline influences external messaging by aligning public summaries with technical nuance. As a result, expectations evolve gradually in parallel with evidence rather than oscillating in response to isolated announcements. The broader research ecosystem also integrates ethical and philosophical reflection regarding the implications of detection. These considerations do not drive methodology, but inform protocols for verification, dissemination, and response. Recognition that claims may carry cultural and existential resonance encourages additional layers of scrutiny. Independent teams replicate analyses using separate datasets and alternative assumptions. Only through such convergence does confidence increase incrementally. Meanwhile, computational modeling advances enable simulation of complex planetary systems with higher fidelity. Coupled climate chemistry and interior models explore feedbacks across scales and assess sensitivity to initial conditions. These simulations generate ensembles rather than single trajectories, reflecting inherent uncertainty. Ensemble behavior highlights robust patterns that persist despite variation. Such robustness guides observational prioritization by identifying signatures least sensitive to confounding variables. The interplay between simulation and observation thus becomes iterative, with each informing refinement of the other. As detection thresholds approach fundamental noise limits, further progress depends on innovation in materials optics and signal processing. Incremental improvements accumulate through sustained engineering rather than abrupt transformation. This mirrors the broader search itself, a gradual convergence toward greater discriminatory power. In this environment, proximity to discovery cannot be measured by calendar or distance. It is expressed through readiness, the degree to which frameworks, instruments, and interpretive discipline are prepared to recognize unfamiliar organization without distortion. Readiness increases as ambiguity is reduced and criteria become operational rather than aspirational. Yet readiness does not imply inevitability. The existence of life beyond a single world remains an open question, bounded by evidence rather than expectation. The ongoing effort accepts this openness as a stable condition rather than a temporary gap. Through patient accumulation, careful constraint, and methodological coherence, the search maintains direction without urgency. It proceeds as a continuous extension of natural inquiry, grounded in repeatable observation and conservative inference. When and if recognition occurs, it will emerge from this continuity rather than interrupt it. Until then, the process itself constitutes progress, quietly refining humanity's understanding of the environments that exist beyond immediate familiarity. As attention continues to broaden, the interpretation of proximity increasingly incorporates limits imposed by cognition and instrumentation rather than by distance alone. Recognition depends not only on what is present, but on what can be distinguished from background variation using available conceptual categories. Human classification systems arise from terrestrial experience and are therefore shaped by a narrow sample of natural phenomena. This constraint is acknowledged within astrobiological discourse through deliberate expansion of operational definitions. Life is framed as a process rather than a substance, emphasizing maintenance of organization, energy management, and continuity over replication alone. Such framing allows consideration of systems that may not resemble familiar cellular structures, yet exhibit comparable functional properties. However, functional inference requires observation of dynamics over time, which remains challenging at interstellar scales. Most current measurements integrate signals across large spatial regions and extended durations. Temporal resolution sufficient to observe adaptive response or regulation is limited. This limitation shapes interpretive thresholds and encourages restraint. Rather than asserting presence or absence, inquiry focuses on compatibility between observed conditions and known requirements for sustained complexity. Compatibility does not equate to realization. It indicates that no immediate physical barrier is evident within the resolution of available data. This distinction is maintained consistently across analytical frameworks. Within planetary atmospheres, chemical disequilibrium serves as one such compatibility indicator. Sustained imbalance implies ongoing processes counteracting equilibration. These processes may be geological, photochemical, or potentially biological. Disentangling their relative contributions requires auxiliary information regarding surface conditions, internal heat flow, and stellar environment. As such, atmospheric analysis is rarely isolated. It is embedded within multi-parameter models that assess plausibility across interacting domains. These models are updated iteratively as new observations constrain inputs. The resulting refinement reduces uncertainty margins while preserving openness to revision. At the same time, planetary surface characterization remains limited. Direct imaging of surface features at meaningful resolution lies beyond current capability for most targets. Indirect inference through albedo variation, phase curves, and polarization provides partial insight. These techniques suggest heterogeneity without specifying composition or function. Interpretation therefore remains conservative, emphasizing what cannot be excluded rather than what must be present. Subsurface environments further complicate assessment. On several bodies within the local planetary neighborhood, evidence supports the existence of liquid layers beneath insulating shells. These environments are shielded from radiation and experience stable pressure regimes. Energy sources such as tidal heating or radiogenic decay may sustain chemical gradients. While such settings are inaccessible to remote detection, their plausibility informs broader expectations regarding where organized chemistry might persist. Yet plausibility alone does not motivate assertion. It motivates targeted exploration when feasible and careful extrapolation when not. The concept of proximity thus shifts from spatial closeness to epistemic readiness. Readiness encompasses the alignment of detection methods, interpretive criteria, and theoretical models. As alignment improves the likelihood of recognizing unfamiliar organization, increases even if that organization remains rare or subtle. Conversely, misalignment can render even nearby phenomena effectively invisible. This recognition informs strategic planning, emphasizing diversity of approach and redundancy of observation. Multiple methods probing different aspects of planetary systems reduce dependence on any single indicator. They also allow cross-correlation, which strengthens inference. In this context, progress is measured through reduction of blind spots rather than accumulation of confirmations. Blind spots shrink as parameter space is mapped and constrained. Areas once unobservable become accessible through incremental technical advance. Others remain inaccessible and are acknowledged as such without extrapolation. This transparency maintains internal consistency and guards against overinterpretation. As inquiry advances, the question of life beyond a single world remains open, yet increasingly well-framed. The framing itself constitutes a form of closeness. Not a closeness defined by imminent discovery, but by the maturity of the questions being asked. Questions that are precise, bounded, and operational. Such questions allow answers to be recognized when evidence eventually supports them. Until that point, the search proceeds without urgency, sustained by methodological continuity and an acceptance of uncertainty as an intrinsic feature rather than an obstacle. In this steady progression, proximity is understood not as anticipation, but as preparedness grounded in cumulative understanding. As the search advances further into refinement, the notion of proximity becomes increasingly disentangled from expectation and instead anchored to resolution and discrimination. Resolution determines the smallest variations that can be reliably separated from noise. Discrimination determines whether those variations can be assigned to distinct underlying processes. Both are constrained by physical limits of measurement and by the interpretive frameworks applied to data. Progress in one without the other yields limited insight. Thus, development proceeds in parallel across hardware theory and analytical practice. Improvements in detector sensitivity expand the range of observable phenomena, while advances in modeling clarify how those phenomena might arise. Neither alone is sufficient. Together, they gradually reduce ambiguity. This reduction does not guarantee recognition of life. It enhances the capacity to identify conditions under which life as a process would be physically sustainable. Such capacity is cumulative and irreversible. Once achieved, it persists across observational campaigns. The gradual narrowing of uncertainty bands around planetary properties illustrates this effect. Mass, radius, density, and orbital parameters, once broadly estimated, are now constrained with increasing precision. Each refinement removes classes of implausible scenarios. As implausibility shrinks, compatibility becomes more sharply defined. Compatibility remains distinct from confirmation, but it is a necessary precursor. Within this landscape, silence carries interpretive value. Extended absence of expected indicators within well-characterized environments informs theories of rarity and emergence. These theories remain descriptive rather than predictive. They outline distributions without asserting inevitability or exception. The persistence of silence across certain regimes suggests that the transition from chemistry to biology may require conjunction of factors that is neither trivial nor universal. This inference is held cautiously without extrapolation beyond available evidence. At the same time, the diversity of environments identified across planetary systems challenges overly narrow assumptions. Worlds once considered marginal now occupy central positions in comparative analysis. This expansion of scope reflects adaptive learning rather than revision of core principles. Physical laws remain constant. Their expression across varied contexts reveals unanticipated configurations. Understanding these configurations improves discrimination between background complexity and organized persistence. In this way, proximity to recognition is improved not by approaching an object but by refining perception. Perception here denotes the integration of data theory and constraint. As perception sharpens, ambiguity recedes. What remains unresolved becomes explicitly bounded rather than vaguely assumed. This bounded uncertainty is a stable state within scientific inquiry. It allows progress without resolution and coherence without closure. Thus, the search continues not toward an endpoint, but toward increasing clarity of what constitutes meaningful evidence. When evidence eventually aligns with criteria refined through this long process, recognition will occur as a natural extension of established understanding rather than as an abrupt revelation. Until then, proximity is measured through preparedness, patience, and cumulative refinement, sustained across time. As the conceptual landscape stabilizes, the role of comparative analysis becomes more pronounced. Comparison allows individual observations to be situated within broader distributions, rather than interpreted in isolation. Planetary properties acquire meaning when contrasted against ensembles, rather than evaluated as singular cases. Ensembles reveal patterns, gradients, and outliers that inform theoretical expectations without dictating them. Within these distributions, certain combinations of parameters recur with notable frequency. Others appear sparse or absent. Such patterns guide inference regarding formation pathways and evolutionary pressures. They do not imply intent or optimization. They reflect the statistical outcome of physical processes operating under constrained conditions. In this framework, rarity is not synonymous with impossibility. It indicates that specific configurations require conjunction of variables that seldom align. Understanding this distinction prevents misinterpretation of frequency as value. The presence or absence of life remains decoupled from notions of centrality or importance. It is treated as an outcome contingent upon physical history, rather than as a defining feature of planetary systems. Comparative study also illuminates degeneracy, where distinct processes produce similar observable effects. Degeneracy complicates interpretation by allowing multiple explanations to coexist. Resolving degeneracy requires auxiliary data or alternative measurement strategies. Thus, observational programs are designed to probe orthogonal parameters, reducing overlap between explanatory domains. For example, thermal structure, atmospheric composition, and orbital dynamics may be assessed jointly to constrain interpretation. No single parameter is granted decisive weight. This multidimensional approach aligns with the complexity of the systems under study. Complexity here denotes interaction rather than intricacy. Simple rules interacting over time generate emergent behavior that resists linear attribution. Recognizing this property informs cautious attribution of causality. In particular, the temptation to associate chemical complexity directly with biological activity is resisted. Complex chemistry arises naturally under a wide range of conditions. Biology represents one subset of such outcomes characterized by persistent adaptation and regulated exchange. Detecting these features remotely remains challenging. Thus, emphasis remains on identifying conditions under which such regulation could be sustained rather than asserting its presence. This emphasis shapes both observation and interpretation. It privileges long-lived environments with stable energy flow and material cycling. Short-lived transients receive less interpretive weight unless contextualized within broader patterns. The accumulation of comparative datasets gradually sharpens this prioritization. Targets once considered equivalent diverge in relevance as distinctions emerge. Such divergence is welcomed as it refines focus without foreclosing alternatives. Throughout this process, uncertainty is not eliminated. It is structured. Structured uncertainty allows clear articulation of what is known, unknown, and unknowable within current limits. This articulation supports strategic decision-making regarding resource allocation and methodological development. As a result, the search maintains coherence despite absence of definitive detection. Coherence derives from internal consistency rather than external validation. In this state, proximity to finding life is conceptual rather than temporal. It reflects the degree to which evidence, if encountered, could be recognized without distortion or overinterpretation. Recognition requires criteria refined through comparison, constraint, and repetition. These criteria mature slowly as datasets expand and models converge. The maturation itself constitutes progress independent of outcome. Whether life beyond a single world is ultimately detected or remains unobserved, the framework developed through this search retains value. It enhances understanding of planetary systems and the processes that shape them. In this sense, the endeavor yields insight regardless of resolution. Advancing knowledge through disciplined comparison and cumulative refinement, while maintaining openness to revision as an enduring feature of scientific inquiry. As synthesis deepens, the interpretive emphasis increasingly rests on convergence rather than signal strength alone. Convergence arises when independent measurements, approaches, and models align toward compatible conclusions without reliance on a single dominant indicator. This alignment reduces susceptibility to error introduced by local assumptions or methodological artifacts. In planetary investigation, convergence may involve agreement between atmospheric composition models, interior structure simulations, and orbital stability analyses. Each component constrains the others, forming a coherent explanatory envelope. Within such envelopes, compatibility with sustained chemical organization can be assessed with greater confidence. This does not establish presence. It establishes that multiple independent constraints do not contradict one another. Such non-contradiction is a prerequisite for meaningful inference. The refinement of convergence criteria has been gradually shaped by lessons from earlier interpretive challenges. Historical cases, where initial signals were later attributed to non-biological mechanisms, reinforce the necessity of layered confirmation. These cases are not treated as setbacks. They function as calibration points informing future evaluation. Through them, thresholds for confidence become more precisely articulated. Confidence here is probabilistic and conditional rather than declarative. It scales with the number and independence of supporting constraints. As thresholds rise, claims become correspondingly rarer. This rarity reflects methodological maturity rather than diminishing opportunity. At the same time, the domain of inquiry expands as new classes of targets are identified. Planets orbiting cooler, longer-lived stars present extended temporal windows for chemical evolution. However, these environments introduce additional variables such as stellar activity and tidal locking. Models incorporate these factors to assess surface and subsurface stability. Results indicate a spectrum of outcomes rather than uniform exclusion. Such diversity reinforces the need for case-specific analysis grounded in common principles. In parallel, advances in computational capacity enable exploration of parameter spaces previously inaccessible. High-dimensional models simulate coupled processes across climate chemistry and interior dynamics. While individual simulations do not predict reality, they reveal sensitivities and dependencies that guide interpretation. Patterns emerging across ensembles inform expectations regarding robustness and fragility of potential biosignatures. Robust features persist across varied assumptions. Fragile features depend on narrow conditions and are treated with caution. This differentiation supports prioritization in observational strategy. Resources are directed toward indicators least likely to arise through non-biological coincidence. Even then, interpretation remains provisional. Provisionality is not a weakness. It is an explicit acknowledgement of the inferential distance between observation and conclusion. Maintaining this acknowledgement preserves coherence and adaptability. As new data arrive, provisional assessments are updated rather than defended. This adaptive posture distinguishes cumulative inquiry from advocacy. Within this posture, proximity to discovery is reframed as reduction of inferential distance. Distance shrinks as uncertainty margins narrow, and explanatory degeneracy is resolved. Resolution does not require certainty. It requires sufficient constraint that alternative explanations become implausible within established frameworks. Achieving such constraint is a gradual process dependent on sustained observation and methodological diversity. It cannot be accelerated without compromising rigor. Thus, timelines remain open-ended, aligned with the pace of evidence rather than expectation. In the absence of definitive recognition, the process itself yields secondary insights. Understanding of planetary formation, atmospheric evolution, and chemical diversity deepens independently of biological outcome. These insights feed back into broader scientific domains, enriching contextual knowledge. The search thereby functions as an integrative enterprise linking disciplines through shared questions and methods. Whether life beyond a single world is ultimately observed remains unresolved. What continues to advance is the capacity to ask the question with increasing precision. Precision reduces ambiguity and clarifies what constitutes meaningful evidence. In this clarity lies a form of closeness grounded not in anticipation, but in preparedness. Preparedness, sustained through convergence discipline and cumulative refinement across extended temporal horizons. As inquiry persists toward deeper integration, the influence of scale becomes increasingly evident across all interpretive layers. Scale governs not only spatial resolution, but also temporal sensitivity, energetic thresholds, and statistical relevance. Phenomena that appear negligible at one scale may dominate behavior at another. This principle informs how planetary environments are assessed and compared. Microscopic chemical interactions aggregate into macroscopic atmospheric patterns, which in turn influence planetary climate over extended durations. Recognizing this hierarchy prevents reduction of complex outcomes to isolated variables. Instead, models incorporate multi-scale coupling, where local reactions influence global states and global states feedback into local conditions. Such coupling is computationally demanding, yet essential for coherent interpretation. Without it, signals may be misattributed or dismissed due to incomplete contextualization. As computational methods evolve, approximations give way to more integrated representations. These representations remain simplified relative to reality, yet capture key dependencies with increasing fidelity. Fidelity enhances discrimination by clarifying which outcomes are robust across scales and which depend on narrow assumptions. Robust outcomes inform general principles, while fragile ones remain case-specific. This distinction guides both theoretical focus and observational design. Observations seek to test robustness rather than pursue singular anomalies. Anomalies are documented but interpreted cautiously until contextualized within broader patterns. This approach reduces susceptibility to confirmation bias and preserves interpretive neutrality. Within this framework, proximity to recognition is associated with the alignment of scale-appropriate evidence and scale-appropriate interpretation. Signals observed at planetary scales must be evaluated using models capable of resolving processes at those scales. Applying mismatched frameworks introduces error regardless of signal quality. Thus, methodological alignment across scales becomes a core criterion of readiness. Readiness also encompasses the ability to integrate null results coherently. Null results refine scale-dependent constraints by eliminating ranges of parameter space without invoking absence. Elimination narrows focus while maintaining openness. This disciplined narrowing accumulates gradually through sustained survey rather than targeted pursuit. Survey strategies map environments comprehensively, establishing baselines against which deviation can be measured. Deviation gains meaning only relative to baseline. Without baseline, variation cannot be contextualized. Accordingly, extensive catalogs of planetary properties serve as reference distributions rather than endpoints. These distributions evolve as detection thresholds improve. Early biases introduced by selection effects are progressively corrected through expanded coverage. Correction alters apparent frequencies and reshapes theoretical expectations. Such reshaping is treated as normal adaptation rather than revision of principle. Principles remain grounded in physical law while expectations adjust to empirical pattern. As these patterns stabilize, they inform probabilistic statements regarding compatibility and persistence. Probability here reflects distribution across known systems rather than prediction of individual outcomes. This probabilistic framing aligns with the inherent uncertainty of remote inference. It avoids overextension beyond evidentiary support. At the same time, it provides a structured basis for assessing relative likelihoods across environments. Likelihood guides prioritization without asserting destiny. In this sense, proximity to finding life is reframed as proximity to statistical clarity. Clarity regarding where sustained chemical organization is more or less compatible with observed conditions. Such clarity supports strategic planning and resource allocation while maintaining epistemic humility. Humility persists as a central orientation, acknowledging that unknown unknowns remain. These unknowns are not invoked to justify speculation. They are acknowledged as boundaries of current understanding. Boundaries motivate continued observation and model refinement rather than premature conclusion. As long as boundaries are explicit, inquiry remains coherent. Coherence sustains long-term effort even in absence of decisive outcome. Thus, the search continues as an exercise in disciplined perception, refining scale alignment, resolving ambiguity, and integrating evidence across domains. Through this process, readiness increases independent of discovery. Readiness defined by the capacity to recognize meaningful deviation when and if it arises without distortion, amplification, or denial. In this sustained alignment between scale evidence and interpretation, proximity is achieved not through anticipation, but through preparedness anchored in cumulative understanding. As understanding accumulates, the interpretive focus subtly shifts toward resilience of conclusions under perturbation, rather than maximal sensitivity to individual measurements. Resilience refers to the degree to which an inference remains stable when assumptions are adjusted within reasonable bounds. An inference that collapses under minor modification is treated as provisional and weak. An inference that persists across varied models, datasets, and analytical choices gains credibility without becoming definitive. This emphasis on resilience reflects recognition that complex systems rarely yield unambiguous signatures. Instead, they produce patterns whose significance emerges only through sustained consistency. Within planetary science, resilience is tested by varying parameters such as stellar spectra, atmospheric chemistry, surface reflectivity, and internal heat flow. If compatibility with sustained chemical organization remains across these variations, confidence in that compatibility increases. This process does not assert realization. It refines the map of possibility. Mapping possibility with resilience in mind prevents overinterpretation of narrow scenarios and supports adaptive revision. Adaptive revision is integral to long-term inquiry. As new data-constrained parameters, previously free models are recalibrated. Recalibration may reduce or expand compatible regimes without invalidating underlying methodology. This dynamic adjustment distinguishes robust frameworks from static ones. Static frameworks risk obsolescence when confronted with unexpected evidence. Robust frameworks absorb novelty by integrating it into existing structure. This capacity is essential when exploring domains beyond direct experience. The unknown is approached through structured openness rather than speculative extension. Structured openness balances receptivity with constraint, ensuring that novelty informs rather than destabilizes interpretation. In practice, this balance manifests through layered confidence language, explicit uncertainty quantification, and separation between observation and inference. Observations are reported with precision regarding measurement context. Inferences are articulated conditionally, referencing the assumptions under which they hold. Such articulation enables downstream reassessment as assumptions evolve. Within this architecture, proximity to recognition is associated with the shrinking gap between observation and inference. Gap here denotes the number and magnitude of assumptions required to connect data to interpretation. As gap narrows, interpretation becomes more direct and less contingent. Narrowing occurs through improved instrumentation, expanded datasets, and refined theory. Each element contributes incrementally. Instrumentation reduces noise and increases resolution. Datasets provide statistical context. Theory clarifies causal pathways and eliminates implausible mechanisms. None alone suffices. Together, they gradually compress the inferential gap. Even then, complete closure may remain unattainable. The presence of life beyond a single world may elude definitive detection despite extensive refinement. This possibility is acknowledged without discouragement. The value of the search is not contingent upon outcome. It lies in the coherence and depth of understanding generated along the way. Understanding of planetary atmospheres, climates, interiors, and chemical diversity advances regardless of biological detection. These advances inform broader questions regarding system evolution and stability. Thus, the search operates within a dual horizon. One horizon concerns the specific question of life beyond a single world. The other concerns general understanding of complex natural systems. Progress in the latter is assured. Progress in the former remains open. Maintaining clarity between these horizons prevents conflation and preserves methodological integrity. As inquiry continues, the pace remains deliberate. Deliberation is not inertia. It is alignment with the temporal scale of the phenomena under study. Phenomena unfolding over billions of years cannot be resolved through haste. They require patience matched to their scale. This patience is institutionalized through long-term missions, sustained funding, and intergenerational knowledge transfer. Such continuity enables cumulative refinement without loss of context. Context ensures that new findings are integrated coherently rather than isolated. Coherence supports resilience, which in turn supports readiness. Readiness here denotes the capacity to recognize significance without distortion when evidence eventually warrants. Until then, the search remains a disciplined exercise in observation, modeling, and inference, proceeding steadily, without urgency, without assertion, and without closure. Anchored in the understanding that proximity is defined not by imminence, but by preparedness cultivated through sustained refinement and resilient interpretation across time. As inquiry approaches greater conceptual closure without resolution, the cumulative effect of restraint becomes increasingly evident. Restraint shapes not only interpretation, but also expectation, regulating the emotional and cognitive framing of the search itself. By maintaining neutrality toward outcome, the investigative process avoids directional bias that could distort analysis. This neutrality is reinforced through procedural checks, replication, and transparency, ensuring that results are evaluated on evidentiary grounds alone. Within this environment, proximity is not measured by signals detected, but by the integrity of the pathway through which detection would be validated. Validation pathways are constructed deliberately with predefined criteria, thresholds, and escalation protocols. Such construction ensures that recognition, if it occurs, is not improvised, but emerges through established channels. These channels integrate observational confirmation, theoretical consistency, and independent verification. Only when alignment persists across these dimensions does interpretation advance. This disciplined architecture reduces susceptibility to false positives and preserves confidence in eventual conclusions. As models mature, they increasingly incorporate uncertainty as a quantified parameter rather than an implicit caveat. Quantification allows uncertainty to be propagated through analyses, revealing how conclusions depend on underlying assumptions. This visibility strengthens interpretive rigor and supports comparative evaluation across studies. Studies with narrower propagated uncertainty carry greater weight without claiming certainty. Those with broader uncertainty inform boundary conditions rather than focal conclusions. Together, they define the landscape of current understanding. Within this landscape, silence and ambiguity are not anomalies. They are expected features reflecting the scale and complexity of the systems under study. Acceptance of these features prevents interpretive fatigue and sustains long-term engagement. Engagement persists through institutional memory, collaborative continuity, and incremental methodological advance. As generations of researchers contribute, refinement accumulates even as individual careers conclude. This intergenerational continuity mirrors the temporal scale of the question itself. Questions spanning cosmic history cannot be resolved within singular observational epochs. They require accumulation across time. Thus, proximity is inherently collective and longitudinal. It emerges from sustained coherence rather than episodic breakthrough. In this sustained coherence, the search remains active without urgency, focused without fixation, and open without speculation. Prepared to recognize significance should it arise, and equally prepared to continue refining understanding should it not. In this balance, the inquiry maintains its integrity, advancing steadily through clarity, discipline, and cumulative alignment across evidence, theory, and method. As the trajectory of investigation continues, the emphasis increasingly settles on continuity as an operational principle rather than a conceptual ideal. Continuity ensures that inquiry does not fragment into isolated efforts, but remains a coherent progression where each contribution inherits context from those preceding it. This inheritance stabilizes interpretation by anchoring new observations within established frameworks, while allowing those frameworks to evolve through incorporation rather than replacement. Such evolution preserves internal consistency and reduces interpretive volatility. Within the search for organized systems beyond a single environment, continuity manifests through sustained monitoring, archival preservation, and methodological inheritance. Observational programs are designed with overlap rather than succession, ensuring that transitions between instruments do not introduce discontinuities in data interpretation. Calibration chains link past and present measurements, allowing trends to be assessed across extended durations. These chains are essential when signals of interest may emerge slowly or fluctuate subtly over time. Without continuity, such signals would dissolve into noise or be misinterpreted as artifact. Continuity also governs theoretical development. Models are not discarded wholesale when challenged, but adjusted through constrained revision. Parameters are updated, boundary conditions refined, and assumptions reevaluated, while core physical principles remain stable. This approach maintains coherence across generations of modeling and prevents oscillation between incompatible explanatory regimes. In this environment, proximity to recognition is not associated with novelty, but with persistence. Persistent patterns acquire interpretive weight precisely because they endure across methods, datasets, and analytical perspectives. Endurance signals robustness even in absence of explanation. Such robustness invites focused investigation without presumption. At the same time, absence of persistence tempers enthusiasm and redirects attention toward alternative interpretations. This dynamic balance is sustained through continuity of practice rather than episodic intervention. Educational transmission reinforces this balance by embedding norms of restraint and replication within training structures. Early career researchers inherit not only data and models, but also interpretive discipline. Discipline shapes how uncertainty is treated, how claims are framed, and how ambiguity is communicated. This inheritance ensures that inquiry remains cumulative rather than competitive. Cumulative inquiry values alignment over priority and coherence over acceleration. Within such a culture, proximity is experienced as gradual convergence rather than imminent discovery. Convergence manifests through narrowing interpretive variance and increasing agreement on criteria rather than on conclusions. Criteria define what would constitute meaningful evidence even when such evidence remains absent. Defining criteria in advance is a critical aspect of preparedness. Preparedness ensures that recognition, if it occurs, is not ambiguous or contested beyond resolution. It establishes shared standards against which claims are evaluated. These standards evolve slowly, informed by past misinterpretations and emerging capabilities. Their evolution reflects learning rather than correction. As standards mature, the search becomes increasingly self-consistent. Self-consistency does not imply closure. It implies readiness to incorporate new evidence without destabilization. In this stable yet open state, inquiry continues without urgency. Urgency would distort temporal alignment between question and method. The question concerns processes unfolding over immense intervals. Method must therefore operate on commensurate timescales. Continuity provides this temporal alignment, allowing gradual accumulation of insight without forcing resolution. Through continuity, proximity is redefined not as nearing an endpoint, but as sustaining an approach capable of recognition. Recognition here denotes the capacity to distinguish significance from coincidence without reliance on expectation. Such capacity emerges only through extended practice, disciplined comparison, and inherited context. Thus, the search advances quietly, embedded within continuity rather than driven by anticipation. Advancing understanding regardless of outcome and maintaining coherence across time as its defining achievement. As the framework reaches greater internal alignment, attention subtly turns toward limits that remain irreducible despite refinement. Some limits arise from physical law, such as finite signal speed, quantum noise, and thermodynamic bounds on measurement. Others arise from perspective, the inherent constraint of observing complex systems from external vantage points without direct interaction. These limits are not obstacles to be overcome, but conditions to be accommodated within interpretive design. Accommodation involves acknowledging where inference must remain probabilistic and where certainty is unattainable regardless of technological advance. In the search for organized systems beyond a single environment, this acknowledgement stabilizes expectations and preserves methodological coherence. Rather than pursuing exhaustive certainty, inquiry defines sufficient conditions under which inference becomes meaningful within stated bounds. Meaningfulness here is operational rather than absolute. It denotes that conclusions follow logically from premises without hidden amplification or omission. This operational clarity allows findings to be integrated across studies, even when definitive answers remain elusive. Integration across studies builds a layered understanding where partial insights accumulate without requiring total resolution. Such accumulation is evident in how planetary environments are now contextualized within galactic structure formation history and stellar population dynamics. These contexts inform probability distributions without asserting individual outcomes. They reveal gradients of opportunity shaped by material abundance, radiation fields, and temporal stability. Opportunity remains distinct from realization. Maintaining this distinction is central to interpretive restraint. Within this restrained posture, the notion of proximity becomes increasingly abstract, yet more precise. It refers to the alignment between what can be observed, what can be modeled, and what can be inferred without contradiction. As alignment improves, the space of plausible interpretation narrows. Narrowing does not converge toward a predetermined answer. It converges toward clarity regarding which answers would be compatible with accumulated evidence. This clarity allows negative results to be integrated productively rather than treated as absence of progress. Progress is reframed as reduction of ambiguity and sharpening of inference. This reframing sustains inquiry across extended durations, even when outcomes remain indeterminate. Institutional structures reflect this reframing by valuing long-term datasets cross-mission synthesis and methodological rigor over isolated claims. Such valuation reinforces continuity and resilience across the research ecosystem. As generations contribute refinement, the collective capacity to recognize significance increases, even if significance remains hypothetical. In this sense, proximity is cumulative and distributed across time and community. It is not experienced as a moment approaching, but as a state gradually achieved. A state in which evidence, if encountered, could be interpreted with confidence proportional to its support. Until that state is fully realized, inquiry proceeds, without urgency, grounded in acceptance of limits and commitment to coherence. The search thus continues as a disciplined engagement, with the unknown shaped by acknowledgement of what cannot be known as much as by pursuit of what might be discovered. As inquiry advances within these acknowledged limits, a complementary emphasis emerges on interpretive patience as a functional necessity rather than a philosophical preference. Patience here denotes the willingness to allow evidence to accumulate across appropriate temporal spans without forcing premature synthesis. For phenomena governed by slow planetary and stellar evolution, meaningful patterns may only become apparent after extended observation. Short-term variability can obscure long-term structure, leading to misclassification if evaluated in isolation. Accordingly, analytical frameworks privilege datasets with temporal depth and prioritize continuity over immediacy. This preference shapes mission planning, data curation, and funding horizons, aligning institutional behavior with the scale of the question. Within this alignment, proximity is reframed as temporal coherence rather than chronological closeness. Coherence develops as successive observations reinforce or constrain prior interpretations without contradiction. Contradiction prompts revision rather than abandonment, preserving continuity while incorporating correction. This process depends on stable reference frames against which change can be measured. Reference frames include baseline atmospheric compositions, orbital parameters, and stellar activity profiles. As these baselines solidify, deviations acquire interpretive significance. Deviation alone does not imply biological relevance. It indicates change requiring explanation within the established framework. Explanations are evaluated against known physical and chemical mechanisms, with preference for parsimony. Only when parsimonious mechanisms fail to account for persistence and pattern does interpretation cautiously expand. This cautious expansion preserves methodological integrity and prevents overextension. The discipline required for such restraint is sustained through communal norms, peer evaluation, and iterative replication. Replication across independent teams and instruments functions as a stabilizing filter, reducing susceptibility to localized error. Stability of inference increases as replication accumulates even when conclusions remain provisional. This stability allows the research community to invest in refinement rather than constant reevaluation. Investment supports development of more precise instruments targeted at resolving remaining ambiguities. As ambiguity narrows, interpretive patience becomes increasingly rewarded through clarity. Clarity here does not equate to discovery. It equates to understanding the boundaries within which discovery could be meaningfully claimed. These boundaries are articulated explicitly through criteria, thresholds, and validation sequences. Articulation ensures that recognition, if it occurs, follows an anticipated pathway rather than an improvised response. Improvisation risks inconsistency and erosion of confidence. Prepared pathways preserve coherence under scrutiny. Such preparedness reflects maturity of the field rather than imminence of outcome. Maturity is characterized by alignment between question method and expectation. Expectation is calibrated to evidence rather than desire. Within this calibration, proximity is experienced as steadiness rather than anticipation. Steadiness supports sustained inquiry across uncertainty without fatigue or distortion. As the search continues within this steady posture, it remains open to unanticipated findings while grounded in established principles. Openness does not entail credulity. It entails readiness to integrate novelty through disciplined evaluation. This readiness grows incrementally as frameworks absorb complexity without destabilization. Thus, progress persists even in the absence of definitive detection, advancing understanding of planetary systems and the processes that shape them. In this persistent advancement, the search maintains purpose independent of resolution, sustained by patience, coherence, and cumulative refinement across time. As the process extends further, the integration of absence becomes increasingly explicit within interpretive reasoning. Absence refers not merely to lack of detection, but to structured non-observation within well-defined parameter spaces. When surveys of sufficient sensitivity repeatedly fail to reveal certain indicators across environments where models predict their detectability, this absence acquires explanatory relevance. It constrains hypotheses by eliminating mechanisms that would otherwise produce observable effects. Such constraint is essential for refining theories of emergence, persistence, and distribution. Absence is thus treated as data rather than deficiency. Its incorporation requires rigorous accounting of detection, limits observational biases, and coverage completeness. Only when these factors are transparently documented does non-observation inform inference responsibly. Within planetary investigation, this practice sharpens distinction between environments that are unexplored and those that are explored without corroboration. The former invite further observation. The latter inform theoretical adjustment. This distinction prevents conflation of ignorance with negation. It also prevents inflation of significance where evidence is lacking. By formalizing absence, the field strengthens its internal logic and reduces susceptibility to speculative extension. Speculation remains bounded by what has been systematically excluded. This bounding stabilizes interpretive space and supports cumulative coherence. As coherence strengthens, proximity is understood increasingly as logical closure rather than empirical saturation. Logical closure denotes the degree to which competing explanations have been constrained by evidence and analysis. When closure increases, interpretation becomes more determinate even if outcomes remain unresolved. Determinacy here refers to clarity regarding what evidence would change conclusions and what would not. This clarity is essential for progress because it defines decision points within inquiry. Decision points guide allocation of observational effort and theoretical focus. They also delineate thresholds beyond which further refinement yields diminishing returns. Recognizing such thresholds preserves efficiency and prevents stagnation. Efficiency is not haste. It is alignment between effort and epistemic gain. As the search matures, this alignment improves through experience and feedback. Feedback loops between observation theory and methodology calibrate expectations and refine priorities. Through these loops, the field self-corrects without abandoning continuity. Continuity ensures that corrections integrate rather than disrupt. Integration maintains narrative coherence across extended timescales. This coherence supports sustained engagement even as definitive answers remain absent. Within this sustained engagement, the question of life beyond a single environment is neither foregrounded nor dismissed. It remains embedded within a broader investigation of planetary diversity and system behavior. This embedding reduces pressure for resolution and allows inquiry to proceed on its own terms. Terms defined by evidence constraint and methodological rigor rather than by anticipation. As a result, proximity becomes an emergent property of the investigative system itself. It reflects how well the system is configured to recognize significance should it arise. Configuration encompasses instruments, models, interpretive norms, and communal standards. As these elements align more tightly, readiness increases independent of outcome. Readiness is the stable achievement of the search. It persists regardless of whether detection occurs. In this persistence, the endeavor attains its enduring value, advancing understanding through disciplined incorporation of both presence and absence, maintaining coherence through restraint and continuity, and sustaining preparedness through cumulative refinement across the vast temporal landscape within which the question itself resides. As the inquiry approaches its later stages, the emphasis increasingly rests on synthesis across constrained domains rather than expansion into new conceptual territory. Synthesis here denotes the integration of refined observational results, mature theoretical models, and disciplined interpretive norms into a coherent operational whole. This whole does not resolve the central question. It stabilizes the conditions under which resolution would be meaningful. Stability is achieved when criteria are explicit, methods are aligned, and assumptions are transparent. Within such stability, ambiguity is not eliminated but rendered navigable. Navigable ambiguity allows inquiry to proceed without distortion, even when definitive outcomes remain absent. The accumulation of navigable ambiguity marks a transition from exploratory to consolidative phases of research. In the consolidative phase, attention turns toward ensuring that all components of the investigative system function coherently together. Instruments are evaluated not only for sensitivity, but for compatibility with interpretive frameworks. Models are assessed not only for explanatory power, but for robustness under constraint. Data practices are refined to ensure traceability, reproducibility, and long-term accessibility. These refinements do not generate new signals. They enhance the reliability of interpretation. Reliability is the foundation upon which recognition would rest if recognition were to occur. Without reliability, signals, regardless of strength, would remain equivocal. Thus, proximity is reframed as reliability readiness rather than discovery anticipation. Reliability readiness indicates that the system of inquiry has minimized internal sources of error, bias, and inconsistency. This minimization is never complete, but it reaches thresholds sufficient for confident inference within stated bounds. At these thresholds, further gains in reliability yield diminishing returns relative to cost and effort. Recognizing this balance informs strategic decisions regarding where to invest resources. Investment increasingly favors maintenance, calibration, and synthesis rather than exploratory proliferation. Such prioritization reflects maturity rather than stagnation. It indicates that the field has mapped much of the accessible parameter space and is now refining interpretation within it. Refinement continues through comparative synthesis, identifying which features persist across diverse environments and which are contingent. Persistence across diversity strengthens inference regarding underlying processes. Contingency highlights sensitivity to initial conditions and contextual variation. Both are informative. Together, they define the structure of possibility within which biological processes could emerge or fail to emerge. Understanding this structure is independent of observing life itself. It clarifies the conditions under which life would be physically sustainable and the conditions under which it would be suppressed or transient. This clarification reduces interpretive ambiguity and sharpens expectations without asserting outcomes. As expectations sharpen, the language of inquiry becomes increasingly precise and restrained. Terms are chosen to reflect conditionality rather than implication. This precision supports internal coherence and external communication alike. Coherence here is not rhetorical. It is methodological alignment across evidence, theory, and practice. Alignment ensures that conclusions drawn at one level do not conflict with assumptions at another. Such conflict would undermine reliability and erode readiness. Avoiding conflict requires continuous cross-validation and synthesis. This work is incremental and often invisible, yet it constitutes the core of progress at this stage. Through synthesis, the search attains a state of equilibrium. Equilibrium between openness and constraint, between patience and precision, between uncertainty and clarity. In this equilibrium, proximity is fully decoupled from immanence. It is defined instead by the stability and preparedness of the investigative system. Preparedness means that if evidence consistent with sustained biological organization were to appear, it could be evaluated rigorously, contextualized appropriately, and communicated coherently. Preparedness also means that if such evidence does not appear, the inquiry remains valuable and directed. Value derives from the deepened understanding of planetary systems, chemical diversity, and physical constraints. Direction derives from the clarity of criteria and methods. Thus, the search concludes not with resolution, but with readiness sustained through synthesis, discipline, and cumulative alignment across all domains of inquiry. As synthesis continues beyond consolidation, the emphasis shifts toward maintaining internal equilibrium within the investigative framework, rather than extending scope or accelerating output. Equilibrium here refers to the balanced interaction between observation, interpretation, theory, and limitation. Each component constrains the others, preventing dominance that could distort inference. Observation without theory produces unstructured accumulation. Theory without observation drifts toward abstraction. Interpretation without constraint amplifies bias. Limitation without engagement stalls progress. Sustained equilibrium allows each element to function within its appropriate bounds. Within this balance, the search for organized systems beyond a single environment persists as a regulated process rather than a directional pursuit. Regulation emerges through methodological norms that prioritize consistency, reproducibility, and proportional inference. These norms ensure that no single dataset, instrument, or model acquires undue authority. Authority instead arises from convergence across independent lines of evidence accumulated over time. Time here is not merely duration, but integration. Integration allows findings to be absorbed into existing structures without disruption. Disruption is not avoided when warranted. It is contextualized and tested against the full body of evidence. Only disruptions that persist through such testing alter the equilibrium. This selective permeability preserves stability while allowing adaptation. Adaptation occurs gradually through recalibration rather than replacement. Such recalibration maintains continuity of understanding even as details evolve. In this state, proximity to recognition is defined by the smoothness with which new evidence could be incorporated without destabilizing the system. A system prepared for recognition is one that can absorb significance without amplification or denial. Absorption requires clearly articulated criteria against which evidence is evaluated. These criteria are refined iteratively, informed by prior ambiguity, misinterpretation, and correction. As criteria mature, interpretive variance decreases across the community. Decreased variance reflects alignment rather than consensus. Alignment allows diverse perspectives to operate within shared boundaries, producing compatible conclusions, even when interpretations differ in emphasis. This compatibility supports coherence across publications, missions, and analyses. Coherence is essential for cumulative progress because it ensures that knowledge builds rather than fragments. Fragmentation would render proximity meaningless by dissolving shared standards of recognition. Thus, maintaining coherence becomes a central objective alongside discovery. Coherence is maintained through continuous synthesis review and cross-domain dialogue. Dialogue integrates insights from astronomy, geology, chemistry, and systems science without privileging any single domain. Integration across domains enriches explanatory capacity while reinforcing constraint. Constraint prevents overextension of analogies beyond evidentiary support. Analogy is used as heuristic rather than proof. Its role is to guide inquiry, not to substitute for observation. This disciplined use of analogy reflects maturity of the field. Maturity does not imply completion. It implies stability under uncertainty. Stability allows the search to persist without fatigue, even when outcomes remain unresolved. Fatigue arises when expectations are misaligned with methodological reality. Alignment prevents such fatigue by framing progress in terms of refinement rather than revelation. Within this framing, each incremental advance contributes to readiness regardless of detection. Readiness is measured by the system's ability to discriminate signal from coincidence under defined conditions. As discrimination improves, interpretive confidence increases, even if conclusions remain conditional. Conditionality is not weakness. It is accurate representation of inference under uncertainty. Accurate representation preserves trust within the scientific process and prevents erosion of credibility. Credibility is essential for long-term engagement across generations. Generational continuity ensures that inquiry spans temporal scales appropriate to the question. The question itself concerns processes unfolding across billions of years. Addressing it requires patience, institutional memory, and sustained coherence. Within this extended horizon, proximity is experienced as maintenance of equilibrium rather than approach toward an endpoint. Equilibrium sustains inquiry by balancing openness and restraint, allowing exploration without distortion. As long as equilibrium is preserved, the search remains viable, purposeful, and aligned with its foundational principles. Proceeding steadily within its bounds, accumulating clarity and preparedness without urgency and without presumption. As the inquiry moves forward within this maintained equilibrium, attention turns toward the role of verification as a slow, stabilizing force rather than a decisive event. Verification unfolds through repetition, cross-examination, and sustained scrutiny across independent contexts. It is not an endpoint, but a continuous process that reinforces interpretive reliability over time. In domains where direct interaction with the subject of study is impossible, verification relies on consistency across indirect measures. Consistency must persist despite variation in instrument design, analytical technique, and observational circumstance. When patterns remain stable under such variation, they gain interpretive weight without claiming exclusivity of explanation. This weight informs prioritization rather than conclusion. Prioritization directs further observation and modeling toward areas where explanatory return is greatest. Within the search for organized systems beyond a single environment, verification therefore acts as a filter that gradually refines focus. Signals that fail to reproduce under varied conditions recede from attention without being dismissed as error. They are cataloged, contextualized, and held in reserve pending future capability. Signals that persist invite deeper integration into theoretical frameworks. Integration tests whether observed persistence can be reconciled with known physical and chemical processes. If reconciliation succeeds, biological relevance is deprioritized. If reconciliation fails, uncertainty remains explicitly acknowledged. This explicit acknowledgement prevents premature escalation of interpretation. Escalation would distort the balance between evidence and inference. Maintaining balance requires disciplined pacing and acceptance that some questions remain open despite extensive effort. Within this pacing, proximity is measured through cumulative validation rather than discovery. Validation accumulates through alignment of datasets, reduction of variance, and clarification of causal pathways. Causal pathways need not be fully resolved to support meaningful inference. They must only be constrained sufficiently to exclude implausible mechanisms. Exclusion strengthens interpretation by narrowing the space of explanation. As this space narrows, interpretive clarity increases even if definitive attribution remains elusive. This increase in clarity represents progress independent of outcome. It reflects the maturation of the investigative system rather than the emergence of a particular result. Within such maturation, the role of uncertainty evolves. Uncertainty shifts from a diffuse background condition to a structured component of analysis. Structured uncertainty is quantified, bounded, and propagated through models. This propagation reveals sensitivity and robustness, guiding further refinement. Robust inferences persist across uncertainty bounds. Sensitive ones are flagged for caution. Flagging does not negate their value. It contextualizes their significance within the broader evidentiary landscape. Such contextualization supports coherent synthesis across studies and prevents fragmentation of interpretation. Fragmentation would undermine shared standards of verification and erode collective readiness. Thus, maintaining shared standards becomes a central function of verification practice. Standards evolve through consensus building informed by empirical experience. Experience accumulates through iterative engagement with both success and limitation. Limitations are not external constraints. They are internal features of the inquiry that shape method and expectation. Acknowledging them openly sustains credibility and trust. Trust enables long-term collaboration across institutions and disciplines. Collaboration distributes verification across diverse perspectives, reducing susceptibility to localized bias. Bias mitigation strengthens interpretive resilience. Resilience allows the system to absorb anomalous findings without destabilization. Anomalies are neither ignored nor elevated prematurely. They are examined within the full context of existing knowledge. Only those that persist through extended verification cycles alter prevailing frameworks. Alteration occurs gradually, preserving continuity while incorporating novelty. In this gradualism, proximity is understood as stability under scrutiny rather than immediacy of result. Stability ensures that when and if recognition occurs, it will rest on a foundation of sustained verification rather than isolated inference. Until such recognition, verification continues as a background process, quietly reinforcing readiness and coherence across the evolving landscape of inquiry. As refinement continues, the concept of recognition itself becomes increasingly defined by process rather than outcome. Recognition is not a moment of revelation, but a condition achieved when evidence, interpretation, and validation converge within established bounds. This condition requires that alternative explanations have been systematically constrained, and that remaining interpretations persist under extended scrutiny. Such persistence is rare by design. Rarity reflects the rigor applied rather than the scarcity of phenomena. Within this framework, recognition is inseparable from restraint. Restraint ensures that interpretive thresholds remain high and that confidence scales proportionally with evidentiary support. Scaling confidence in this manner prevents inflation of significance, and preserves coherence across the investigative system. Coherence is essential because recognition carries implications that extend beyond technical domains into broader conceptual understanding. To preserve coherence, recognition must emerge through predictable pathways grounded in prior agreement on criteria and method. These pathways are articulated gradually through accumulated experience rather than codified abruptly. As experience grows, interpretive language becomes increasingly precise. Precision reduces ambiguity by limiting semantic drift between observation and inference. This reduction supports consistency across analyses conducted by independent teams. Consistency strengthens collective understanding even in absence of final attribution. Within the search for organized systems beyond a single environment, such collective consistency represents a form of proximity. It indicates that if a signal were to satisfy established criteria, its interpretation would not fracture along disciplinary or methodological lines. Fracture would indicate unresolved ambiguity within the framework itself. Avoiding fracture requires continuous calibration of assumptions and alignment of terminology. Terminology is refined to distinguish possibility from plausibility and plausibility from support. These distinctions are maintained rigorously to prevent conceptual conflation. Conflation would erode interpretive clarity and undermine readiness. Readiness depends on shared understanding of what constitutes meaningful deviation from baseline expectation. Baseline expectation is constructed through extensive survey and modeling. As baselines solidify, deviations acquire clearer significance. Significance here remains conditional until verified. Verification cycles reinforce or weaken interpretive claims over time. Time thus functions as an active component of recognition rather than a passive backdrop. Extended duration allows transient artifacts to fade and persistent patterns to emerge. Persistence across time carries weight precisely because it resists simple explanation. Yet resistance alone does not imply biology. It implies that known non-biological mechanisms require reassessment or refinement. This reassessment may reveal overlooked processes or confirm existing understanding. Both outcomes contribute to progress. Progress is measured through reduction of unexplained variance and enhancement of explanatory coherence. As coherence improves, interpretive confidence increases without demanding closure. Closure remains optional rather than required. The system is designed to function productively in its absence. This design reflects acceptance that some questions may remain open indefinitely. Openness does not diminish value. It sustains inquiry by allowing continued refinement without frustration. Frustration arises when expectation exceeds methodological capacity. Capacity is expanded gradually through innovation and synthesis. Innovation introduces new tools and perspectives. Synthesis integrates them into existing structures. Integration preserves continuity while enabling advancement. Within this integrated system, recognition, if it occurs, will be absorbed as an extension of accumulated understanding rather than as disruption. Absorption requires that interpretive structures are flexible yet constrained. Flexibility allows accommodation of novelty. Constraint prevents overextension. Balancing these qualities is central to readiness. Readiness signifies that the investigative system has matured sufficiently to distinguish signal from coincident significance from anomaly and evidence from implication. In this matured state, proximity is realized as alignment between method, expectation, and interpretation, rather than as anticipation of discovery. The search thus continues within this alignment, sustained by clarity, patience, and disciplined refinement across time. As the process nears completion, the cumulative discipline embedded within the inquiry reveals its final orientation toward quiet endurance rather than resolution. Endurance here refers to the capacity of the investigative framework to persist intact across uncertainty, without erosion of rigor or purpose. Such endurance is cultivated through alignment of method expectation and interpretive restraint refined over extended durations. Within this alignment, the search for organized systems beyond a single environment becomes sustainable independent of outcome. Sustainability ensures that inquiry does not depend on periodic validation through discovery. Instead, it derives stability from internal coherence and cumulative refinement. This stability allows the question to remain active without imposing pressure for closure. Pressure would distort inference by incentivizing premature synthesis. Avoiding such distortion preserves the integrity of the search across generations. Generational continuity ensures that insight accumulates even as individual contributions conclude. This accumulation is incremental yet irreversible. Once interpretive criteria are refined and validated, they become part of the shared structure of understanding. They do not reset with absence of detection. They persist informing future inquiry regardless of direction. Within this persistent structure, proximity is understood as achieved, not awaited. Achieved through readiness, coherence, and resilience rather than proximity to an event. Event-based framing would misalign with the temporal scale of the phenomena under consideration. Phenomena unfolding across cosmic intervals require frameworks capable of equal duration. Such frameworks privilege endurance over immediacy. Endurance supports patience, and patience supports clarity. Clarity emerges from repeated engagement with ambiguity under consistent constraint. Constraint shapes interpretation by bounding speculation and focusing analysis. Within bounded speculation, creativity remains disciplined and productive. It explores plausible extensions without violating established principles. This disciplined creativity allows inquiry to adapt to novelty without destabilization. Adaptation ensures relevance across changing observational capabilities. As instruments evolve, older data gain new interpretive value through reanalysis. Reanalysis strengthens continuity by linking past and present within a single narrative. Narrative coherence does not impose direction. It preserves context. Context ensures that new findings are integrated meaningfully rather than isolated. Isolation would weaken inference by detaching evidence from accumulated understanding. Thus, endurance and context operate together, sustaining interpretive integrity. As the inquiry rests within this sustained state, readiness becomes its defining achievement. Readiness encompasses the ability to recognize significance without distortion, respond to novelty without overextension, and incorporate absence without erosion of purpose. In this readiness, proximity is no longer a metric of distance or time. It is a condition of preparedness realized through cumulative effort. Preparedness allows inquiry to persist calmly aligned with its foundational principles, regardless of outcome. Whether organized systems beyond a single environment are eventually detected or remain unobserved, the framework built through this search retains enduring value. It deepens understanding of planetary diversity, chemical complexity, and systemic constraint. This deepening constitutes progress independent of resolution. Thus, the inquiry reaches a state of quiet completion not through answer, but through preparedness. Preparedness sustained by endurance, coherence, and disciplined refinement across the vast temporal and conceptual landscape that the question itself inhabits. As continuity persists beyond endurance, the final layers of the inquiry settle into a state defined by quiet operational stability rather than directional movement. Stability here does not imply stasis. It denotes that the mechanisms of inquiry function without internal tension or unresolved contradiction. Observation theory interpretation and limitation coexist in proportion without one exerting undue influence over the others. This proportionality allows the search to continue indefinitely without distortion. Within such stability, the question of organized systems beyond a single environment remains active yet unburdened by expectation. Expectation has been replaced by calibration. Calibration aligns methodological capacity with interpretive ambition, ensuring that conclusions remain commensurate with evidence. This alignment is sustained through continuous internal reference to established criteria validation pathways and uncertainty structures. Uncertainty is no longer an external pressure. It is an integrated component of reasoning that shapes interpretation at every stage. Integration transforms uncertainty from a source of ambiguity into a guide for disciplined inference. Guided inference proceeds within defined bounds, preventing escalation beyond support. Support accumulates through repetition synthesis and resilience under variation. As resilience increases, interpretive structures become more durable even as conclusions remain provisional. Durability supports long-term engagement without fatigue. Fatigue is mitigated by the absence of urgency and by acceptance that some questions do not resolve within human timescales. This acceptance is not resignation. It is methodological maturity. Maturity recognizes that inquiry can be complete in structure without being complete in answer. Completeness of structure ensures that the system is prepared to respond appropriately to any eventual outcome, including continued absence. Absence does not destabilize the system because significance is not contingent upon discovery. Significance derives from coherence, clarity, and cumulative understanding. These qualities persist regardless of empirical resolution. Within this persistent framework, proximity is fully internalized as preparedness. Preparedness encompasses interpretive readiness, methodological alignment, and communal consensus on criteria. Consensus here does not imply uniform belief. It implies shared standards for evaluation and validation. Shared standards allow diverse interpretations to coexist within compatible bounds. Compatibility preserves coherence across the investigative landscape. Coherence enables synthesis across time disciplines and methodologies. Synthesis maintains narrative continuity without imposing direction. Narrative continuity ensures that each contribution builds upon prior understanding rather than fragmenting it. Fragmentation would erode preparedness by dissolving shared reference points. Preparedness, therefore, depends on continuity as much as on innovation. Innovation is absorbed through calibration rather than disruption. Calibration adjusts frameworks, incrementally preserving stability while accommodating novelty. This process mirrors the phenomena under study, which evolve gradually through constrained interaction rather than abrupt transformation. By mirroring this dynamic, the inquiry maintains congruence between method and subject. Congruence enhances interpretive fidelity, reducing the risk of misalignment. Misalignment would amplify noise and distort inference. Avoiding it is central to readiness. As readiness consolidates, the inquiry enters a sustained equilibrium. Equilibrium supports ongoing observation, modeling, and synthesis without pressure for closure. Closure is neither sought nor avoided. It remains contingent upon evidence rather than desire. This contingency preserves integrity and ensures that recognition, if it occurs, will be proportional, grounded, and coherent. Until such recognition or its absence is established beyond revision, the inquiry remains valuable, complete in structure, and stable in purpose. Through this stability, the search attains its final form not as a concluded investigation, but as a durable framework for understanding. a framework capable of enduring uncertainty, integrating absence and recognizing significance, without distortion across the extended temporal horizon that the question itself inhabits. As the inquiry holds within this sustained equilibrium, the final orientation emerges as one of silent continuity rather than culmination. Continuity here signifies that the investigative system has reached a configuration capable of indefinite operation, without internal escalation or erosion. Its processes no longer seek acceleration or expansion. They maintain calibration through repetition verification and incremental refinement. Within this configuration, proximity is no longer discussed explicitly because it has been absorbed into operational readiness. Readiness manifests as the ability to evaluate any new observation within an established lattice of criteria, constraints, and expectations. This lattice is neither rigid nor diffuse. It is structured enough to prevent overinterpretation and flexible enough to accommodate novelty. Flexibility is governed by constraint, ensuring that adaptation does not become drift. Drift would introduce inconsistency and undermine accumulated coherence. Coherence remains the central stabilizing feature binding observation, interpretation, and theory into a unified process. Unity does not imply uniformity. Diverse methods and perspectives operate within shared boundaries, producing compatibility rather than convergence. Compatibility ensures that interpretations can differ in emphasis without conflicting in principle. This non-conflict preserves cumulative progress and prevents fragmentation. Fragmentation would dissolve shared standards and render recognition ambiguous. Avoiding ambiguity requires continuous reinforcement of interpretive norms. These norms are sustained through practice, education, and institutional memory. Memory links past and present, ensuring that lessons from prior uncertainty inform current judgment. Judgment matures through exposure to both confirmation and revision. Revision does not negate prior work. It refines it within narrower bounds. This narrowing clarifies what remains unresolved and why. Clarity regarding unresolved domains prevents misallocation of effort and maintains focus. Focus is directed toward maintaining system integrity rather than forcing outcome. Forcing outcome would violate alignment between method and phenomenon. Phenomena of this scale resist coercion through inference. They yield only through sustained, compatible observation. Compatibility between observation and phenomenon requires patience matched to temporal scale. Temporal scale here exceeds individual lifetimes, necessitating collective continuity. Collective continuity ensures that inquiry transcends individual expectation. Expectation yields to discipline. Discipline sustains inquiry without urgency. Urgency would distort interpretive thresholds and compromise readiness. By eliminating urgency, the system preserves proportionality between evidence and inference. Proportionality is the measure by which interpretive integrity is maintained. Integrity ensures that any future recognition will be credible, coherent, and resilient under scrutiny. Resilience arises from the accumulated structure of the inquiry rather than from isolated findings. Structure persists regardless of empirical outcome. It is the enduring product of the search. Through this persistence, the inquiry achieves a state where absence, presence, and ambiguity are all equally integrated. Integration prevents imbalance and sustains operational calm. Calm is not passivity. It is stability under uncertainty. Within this stability, the search continues not as anticipation, but as maintenance of readiness. Readiness anchored in cumulative understanding, disciplined interpretation, and acceptance of limits. Thus, the inquiry proceeds into its later phase, not seeking closure, but sustaining coherence across time. Prepared to recognize significance without distortion, and equally prepared to continue without resolution within the vast temporal context that defines the question itself. As the inquiry advances within this late phase, the emphasis settles on preservation of interpretive balance across extended horizons rather than achievement of terminal insight. Balance here denotes the sustained proportion between evidence accumulation, theoretical framing, and acknowledgement of constraint. Each element continues to inform the others without escalation or attenuation. This proportion prevents drift toward either overconfidence or paralysis. Overconfidence would compress uncertainty prematurely. Paralysis would treat uncertainty as prohibitive rather than informative. Maintaining balance allows uncertainty to function as a stabilizing parameter guiding inquiry rather than obstructing it. Within this balanced state, the investigative system becomes largely self-regulating. Feedback from observation refines models. Models shape interpretation. Interpretation informs subsequent observation without generating expectation of resolution. Expectation has been replaced by calibration and calibration by endurance. Endurance supports continuity across institutional and generational boundaries. Boundaries are traversed through shared standards, archival integrity, and methodological inheritance. Inheritance ensures that refinement is cumulative rather than repetitive. Each contribution adds constraint, clarity, or coherence without reopening settled ground. Settled ground here refers not to answers, but to frameworks that have proven resilient under scrutiny. Resilience is tested through variation replication and long-term consistency. Frameworks that endure these tests become part of the stable substrate upon which further inquiry rests. This substrate does not dictate outcome. It defines process. Process-oriented inquiry remains viable regardless of empirical result. Viability is sustained by the recognition that understanding planetary systems and their constraints is intrinsically valuable independent of biological detection. This intrinsic value anchors motivation and preserves purpose. Purpose does not depend on milestone achievement. It depends on alignment between question and method. As long as alignment holds, inquiry remains justified. Alignment is maintained through continuous synthesis and review. Review does not seek novelty. It seeks coherence. Coherence ensures that interpretations across time remain mutually intelligible. Intelligibility supports trust within the research community and beyond. Trust allows sustained investment without demand for immediacy. Investment supports maintenance of instruments' data and expertise across long durations. Such maintenance is essential when phenomena of interest evolve slowly or remain subtle. Subtlety requires sensitivity and patience rather than force. Force would distort signal interpretation. Patience allows signal to emerge if it exists without coercion. Within this patience, proximity is no longer framed as approach, but as steadiness. Steadiness reflects the system's ability to remain responsive without reactionary shifts. Reactionary shifts would amplify noise and erode interpretive discipline. Discipline remains the core virtue of the inquiry. It governs how absence is treated, how possibility is articulated, and how plausibility is distinguished from support. These distinctions are preserved meticulously to avoid semantic drift. Drift would blur boundaries and undermine readiness. Readiness depends on clarity regarding what constitutes meaningful deviation from established patterns. Patterns are established through extensive survey and modeling. Deviation gains meaning only when patterns are well constrained. Constraint accumulates gradually through repeated measurement and synthesis. As constraint tightens, interpretive space narrows without collapsing. Collapse would imply forced resolution. Narrowing preserves openness while increasing precision. Precision enhances the capacity to recognize significance without exaggeration. Exaggeration would compromise credibility and destabilize the framework. Avoiding it preserves the quiet integrity of the search. Integrity ensures that inquiry can persist calmly within uncertainty without loss of direction. Direction here is procedural rather than goal-oriented. It follows from adherence to method rather than pursuit of outcome. This procedural direction sustains inquiry across time scales commensurate with the phenomena under consideration. Phenomena shaped by cosmic evolution cannot be rushed into conclusion. They must be engaged through endurance, coherence, and balance. Within this engagement, the inquiry continues not toward an answer, but within preparedness. Preparedness that has been earned through cumulative refinement, disciplined interpretation, and sustained equilibrium across all domains of evidence and inference. As the inquiry approaches its penultimate articulation, the emphasis rests on consolidation of all prior refinement into a stable interpretive posture that neither advances nor retreats, but remains consistently responsive. Responsiveness here refers to the capacity of the investigative framework to accommodate new information without requiring structural revision. This capacity emerges only after prolonged calibration across evidence theory and limitation. Calibration aligns interpretive sensitivity with empirical support, ensuring that the system responds proportionally rather than reactively. Reactive interpretation would distort significance by amplifying novelty beyond constraint. Proportional response preserves coherence and sustains credibility across extended horizons. Within this posture, the search for organized systems beyond a single environment is no longer driven by progression, but by maintenance. Maintenance ensures that accumulated understanding does not degrade through neglect, reinterpretation, or fragmentation. Fragmentation would arise if standards drifted or if interpretive norms weakened over time. Preventing such drift requires continuous synthesis, archival care, and methodological vigilance. Vigilance here is not intensity, it is consistency. Consistency ensures that each new contribution is evaluated against the same criteria that shaped prior understanding. These criteria have been refined through decades of constraint, replication, and correction. They now function as a stable reference lattice within which interpretation operates. Operating within this lattice, proximity is implicit rather than explicit. It is embedded in the readiness of the system to evaluate significance without hesitation or inflation. Hesitation would indicate unresolved ambiguity. Inflation would indicate misalignment between evidence and inference. Avoiding both reflects maturity of the framework. Maturity does not preclude change. It enables controlled adaptation. Adaptation occurs when evidence persistently challenges existing constraints across independent lines. Such challenge is rare by design. Rarity preserves stability while allowing genuine novelty to register. When novelty registers, it is absorbed through established pathways of verification and synthesis. Absorption ensures continuity rather than rupture. Rupture would compromise accumulated coherence and undermine trust. Trust is essential for sustained inquiry because it allows interpretation to unfold without constant revalidation of foundational assumptions. Foundational assumptions here refer to physical law, methodological discipline, and probabilistic reasoning. These assumptions are not immutable. They are resilient. Resilience has been tested through repeated application across diverse contexts. Contexts include varied planetary systems, stellar environments, and chemical regimes. Across this diversity, the core principles have held while specific expectations have adapted. This pattern of stable principle and flexible application underpins the entire search. It ensures that inquiry remains anchored even as observational reach expands. Expansion now proceeds cautiously informed by lessons from earlier phases. Those lessons emphasize the importance of patience, proportionality, and humility. Humility here is operational. It manifests as restraint in inference and clarity in communication. Clarity prevents conflation of possibility with realization and of compatibility with confirmation. These distinctions are preserved rigorously within the mature framework. Preservation supports interpretive health across time. Health denotes the absence of internal contradiction and the presence of clear evaluative pathways. Healthy frameworks sustain engagement without fatigue. Fatigue arises when expectations are misaligned with capability. Capability has now been thoroughly assessed and integrated into interpretive norms. Norms reflect what can be known, inferred, or constrained within current limits. Operating within these norms, the inquiry remains active without pressure. Pressure would distort pacing and compromise balance. Balance remains the defining feature of this late stage. Balance between openness and constraint, between curiosity and discipline, between exploration and consolidation. Within balance, the search achieves a form of quiet completion. Completion not of question, but of preparation. Preparation signifies that the system is fully configured to recognize significance should it arise, and equally configured to persist without erosion should it not. This dual readiness represents the culmination of cumulative refinement. It is not an end point, but a stable state within which inquiry can continue indefinitely. A state defined by coherence, endurance, and disciplined responsiveness across the full scope of evidence and inference accumulated over time. As the inquiry reaches its final articulation, the accumulated structure settles into a state of complete interpretive preparedness, where no further expansion is required for coherence to persist. Preparedness here denotes that every component of the investigative system now operates within clearly defined bounds that have been refined through extended engagement with evidence limitation and synthesis. Observation is calibrated to expectation. Expectation is constrained by method, and method is aligned with the scale and nature of the phenomena under consideration. Within this alignment, the search for organized systems beyond a single environment becomes structurally complete, even as the question itself remains open. Completeness in this sense does not imply exhaustion of possibility. It signifies that the framework required to recognize significance has reached maturity. Maturity is characterized by proportional response to evidence, resilience under uncertainty, and stability across variation. These qualities have been cultivated gradually through disciplined practice, replication, and restraint. Restraint has prevented premature closure, while stability has prevented interpretive drift. Together, they have produced a system capable of enduring absence, presence, and ambiguity without loss of coherence. Coherence here is not narrative convenience. It is methodological integrity maintained across time scales commensurate with cosmic processes. Processes that unfold across vast durations cannot be compelled into resolution. They can only be engaged through frameworks designed for endurance. Endurance has been achieved through cumulative refinement, shared standards, and continuity of interpretation. Continuity ensures that insight persists across generations, linking past, present, and future inquiry into a single coherent process. Within this process, proximity is no longer a variable. It has been internalized as readiness. Readiness to evaluate evidence without distortion, readiness to incorporate novelty without overextension, and readiness to persist without erosion, should definitive recognition remain absent. This readiness reflects the highest attainable state of inquiry under current constraints. It does not anticipate discovery, nor does it preclude it. It establishes conditions under which discovery would be meaningful, credible, and resilient under scrutiny. Such conditions are rare not because phenomena are scarce, but because rigor demands patience, proportionality, and constraint. Through patience, the system has aligned itself with the temporal scale of the question. Through proportionality, it has preserved balance between curiosity and discipline. Through constraint, it has prevented speculation from exceeding support. Together, these qualities define the final posture of the search. A posture of calm stability sustained by cumulative understanding rather than expectation. Within this posture, inquiry remains active without urgency, responsive without reactivity, and open without credulity. It continues as a durable framework capable of integrating future evidence or continued silence with equal coherence. In this durability lies the true completion of the endeavor. Not an answer, but a state of preparedness earned through disciplined refinement across observation, theory, and interpretation. A state in which significance, if encountered, would be recognized without amplification or denial, and in which absence would be integrated without loss of purpose. Thus, the inquiry concludes not by resolving the question, but by fully equipping itself to live with the question across the extended horizon that defines it. A horizon shaped by cosmic time, planetary diversity, and the quiet persistence of structured understanding that endures regardless of outcome.